start kar. Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 169 and 170. So you just check it and keep it there visible and there. Yes, okay. So that will check always. Okay, whether it is sliding down or not. Okay. So if it looks okay here, everything is okay. Thank you very much. Okay, so as today we are into lecture 169 and 170. So we are discussing the Gibbs phase rule and its application. 12 applications we are considering. We are discussing number 6, which actually is the equilibrium. This equilibrium we discussed, okay, and we demonstrated how it is this 0 degree of freedom, and how without having any freedom the system can still be defined in terms of temperature, pressure and composition. This part was already over in the last class. So today we actually the pending work is the stability diagram construction. This I have already shown you by figure 6. 6A is the actually this system, the setup system arrangement. Figure 6A. This you saw last class. Today these three curves 6B, 6C and 6D. Don't think about this, okay? And just ignore this for the time being. It is about example 7. So this is example 6 we are discussing. Example 7. This is the next one. Stability diagram is what I wanted to tell you. Remember, this is actually invariant system, 0 degrees of freedom, and demonstration is complete, and 3 independent reactions, 1, 2, 3. Recall this, and so you actually see these 3 reactions. Stability diagram. Follow 6P. Follow. I'll actually, before I write anything here, you just try to understand. Follow these 3 curves you see. 3 curves. One is, the first is actually your CO2 plus C is 2CO equilibrium. Okay, that curve is what? This one. This one. And I have written somewhere. Here I have shown CO2 C CO curve. And also I have mentioned equation 2, as you see. The next is what? This red one. Red. This one. This I have written here. Which one? This is Fe-Fe3C. This reaction. Fe-Fe3C curve. And also I have mentioned, have I mentioned here Fe-Fe3C curve? So what I have mentioned there. Let me check. This Fe. This okay. This fine. Fe-Fe3C. Very good. No problem. Fe-Fe3C curve. Okay. That actually I could not write this. This is actually equation 3. Equation 3. Fe-Fe3C curve. The red one. I have written Fe-Fe3C curve, but I didn't get space there to write that it is equation 3. But this is equation 3. So 2 curves I have explained, and this is third curve. This is third curve. This is what? Fe-FeO equilibrium. Equilibrium or equation or reaction 1. Equilibrium 1. Fe-FeO. So 1, this is 2, and red is the 3. These 3 curves are shown. You see these 2 curves, that is, this is Fe-Fe3C curve and CO2CCO, means equation 2 and equation 3. Reaction 2 and 3, they actually, this equilibrium curve, they are actually, remember, the plot is percentage CO against temperature. That are the axes, and percentage CO in CO2 mixture. Okay, so these are the actually the axes, and temperature, certain temperatures I have actually highlighted. This span is 673 to 1273. and here it is 0 to 100%, and percentage CO2 is 100 minus percentage CO at any point. So see, follow this. This is this curve, a red curve, Fe-FeO curve, and carbon saturation curve. Okay, we call this also CO2 curve. Activity of carbon is considered 1. And also remember this, I'm sorry that I forgot to mention, these diagrams are drawn for different pressures. So this is, for example, the first one, 6P for P is 1 atmosphere. P is 1 atmosphere. Subsequently, you will see pressure has increased to P is 5 atmosphere in the 6C, and 6D is P is still 10.04 atmosphere. So 3 pressures actually are considered. So CO2 CO curve is already started. You don't have any difficulty. Already this curve I have shown you. And pressure, this is drawn for certain pressure. For example, 1 atmospheric pressure. So the additional curve is this Fe-Fe3C curve. Equation 3. This is additional curve. And of course, Fe-FeO curve, the equation 1. So first we concentrate on these two curves. These two. This and this. This and this means red curve and black curve. Okay, this one. This carbon saturation curve and Fe-Fe3C curve. They intersect at L. And what is that? That refers to the temperature 1037 Kelvin. And what is the corresponding percentage here? 80%. Okay. And also other things I tell you. Another thing I tell you, this carbon curve or carbon saturation curve or CO2 CO curve, this intersects this Fe-FeO curve at this point, and which corresponds to temperature of 966 Kelvin. And what is this? Corresponding percentage CO 59. This is actually this is actually very important in our iron making study. Remember what it says. I tell you, this is actually not very pertinent here, because we are interested to show this invariant situation, 0 degrees of freedom, where I have written here. This culmination of these two, of these three, is this one, the third one, and there you will show this, how this invariant system is represented here graphically, and that will be very, very satisfying, very useful concept, okay, and very useful, okay, study. So please follow this. So, but in passing, you will note that this curve, carbon curve, CO2 CO curve, okay, intersects this Fe-FeO curve at point this, I have not named here, but it shows the 966 Kelvin and 59%. What is the significance of this? I tell you in passing that it says, and pressure is 1 atmosphere. It says carbon can reduce FeO to strike, okay, can reduce at any temperature above 966. This is the meaning. If you want to reduce FeO by carbon, the answer is what temperature you, under 1 atmospheric pressure, what temperature is required. If you want to reduce it, if you actually work at a temperature below 966, you will never be successful. So what you have to do to reduce FeO, and in fact FeO is coming from Fe2O3, you may consider Fe2O3, Fe3O4, and then FeO. So if you take care of FeO, then you take care of Fe2O3 also. So FeO is the most important issue, reduction of FeO by carbon. And the answer to this question is that what temperature is required to reduce FeO solid by carbon under 1 atmospheric pressure. Answer is clear, is this 966 Kelvin, is close to 700 degrees centigrade. And above that, not this, above that actually you will see this carbon curve will be actually, will produce actually more percentage CO, okay, enough CO percentage, CO reducing potential enough, that is percentage CO is more than is required at equilibrium, okay. So that is actually will produce enough CO to reduce FeO to Fe, okay. So this is answer, but this is not our main discussion. Main discussion is we follow step by step. This intersection we follow. Then I will show you the this all three curves 1, 2, 3 will have a common intersection point here, and the third diagram 60. So go step by step. First here you try to understand here what it says. At this point, carbon curve intersects the Fe-Fe3C curve. Carbon curve intersects Fe-Fe3C curve. Carbon curve means CO2CCO. Okay, here in short carbon curve. Okay, or equation 2. So this intersects at point L. What is the significance of this point? Is that at point L, which is by the way, the temperature is 1037 Kelvin as I have said, and its corresponding percentage U is 80%. What it says, at this state of L, these phases are together. They coexist. Who are there? So since it is carbon solid and Fe3C solid, these three solid coexist at this. But we have to make still another phase. FeO solid coexist. So then all four solid will coexist. But you see FeO is down here. And still another thing I tell you, one thing, I have written something you follow. First of all, say go step by step. Suppose this curve, this is say at this temperature, say it goes in any temperature, say at this temperature, above this curve and below the curve. This I discussed some previously perhaps, but you again, if you have forgotten, follow this. Above what this curve represents the say simple one Fe-FeO, the first one, this curve, Fe-FeO curve. So along the curve, this yes I discussed previously a number of times. Along the curve, Fe-FeO both coexist. Above the curve, Fe is stable. Below the curve, FeO is stable. Okay, so this is actually above the curve, Fe is stable, and below the curve, FeO is stable. So what is happening here? And similarly, if you actually follow this red curve, that is also interesting. Follow here red curve. Okay, if we increase the CO percentage, Fe3C will be stable. If we decrease the CO percentage, Fe will be stable. So follow this red curve. I've written here. If we increase CO, means this way along the y-axis, above which is stable, as I have said, Fe3C. So above the curve, Fe3C. Below the curve, as I have said, below CO is decreasing. So above is this way. So Fe will be stable. So below Fe, above Fe3C of the red curve, of this red curve, for Fe-Fe3C equilibrium, and along the curve, both Fe-Fe3C. So you get this, along this curve, red curve, Fe-Fe3C coexist, and along this Fe-FeO curve, this curve, Fe-FeO coexist, and above, below, okay? So below the curve. And this carbon saturation curve, as I have told you, recall that this I discussed actually the example 2 perhaps, okay? Details we discussed, and I told you that this curve, outside this to the left or above is actually unstable zone, shooting zone. This I said, this I have not shown unnecessarily, because our main purpose is to show all phases together under 0 degrees of freedom. No freedom, automatically fixed. This we want to establish through the stability diagram. These are the stability diagram, no doubt. Through this we will show. So follow this. So what I want to show you here, okay, very good. At this point, which phases are coexisting? Along Fe-Fe3C, because the red curve is for Fe-Fe3C, and carbon, this is carbon curve. So Fe-Fe3C carbon coexist at point L. But it doesn't include FeO. FeO is below. Here, see, Fe is stable here. Fe is here. See, above the curve, Fe. Above this curve, Fe. So Fe is here. Fe is here. Fe, Fe3C, C. FeO is below that curve. So not stable, not coexisting at L. Under this condition of P is 1 atmosphere. Now we want to remember these figures also. Another thing you figure, see, at this temperature, by the way, it will be important to note, at this temperature, This temperature got from L 1037. We noted at the same time that what is the percentage of CO when this at this temperature on the Fe-FeO curve. On the Fe-FeO means this curve. This curve, what is the percentage of CO? You clearly read this 63%. This will be useful because you follow this, read this data 63. Okay, but remember they have actually intersected these two curves intersect L, making Fe, Fe3C and carbon coexist, excluding FeO. Then you increase the pressure. The moment you increase the pressure, say you consider this pressure 5 is from 1 atmosphere to 5 atmosphere, again they intersect. Just previous two curves, carbon saturation curve and Fe-Fe3C curve. This red curve and black curve, they intersect. Now again at L, this is the L. The temperature remaining 1037. Pressure has not changed anything about temperature, but what has changed? This value which was 80% CO, previously L, the L has now been down to 68. So change. Now and L and that previously this temperature the heats at this temperature, what is the CO percentage on the Fe-FeO curve? 63 previously and now also, because pressure doesn't change this Fe-FeO curve, has no impact on this equation 1 or Fe-FeO curve, because see 1 mole CO and 1 mole CO2 gas, number of moles of gas actually same, so pressure will not modify anything, okay? Will not change anything, has no effect on this. So the curve has unchanged, Fe-FeO curve unchanged. So we see 63. So what has changed? 80 has been reduced to 68. So what does it mean? We see these 2 points L, what I have said there, this is the L, and what I have said L dash, okay, the temperature at this temperature, the point on the Fe-FeO curve which is 63, this we have marked as L prime. So L prime here also same, the temperature at this temperature on the Fe-FeO curve, this is L prime. So we see 80 has been reduced to 68. It is now and it is now closer to 63. Previously 80 63, now it is 68 63. So this is the modification. So if you further increase the pressure to, this can be actually, this we have already shown how to calculate this. This part is I will not repeat. Okay, wastage of time. I will concentrate on these 3 curves. This is actually, if you further increase to 10.04, then we see this point, this intersection of the 2 curves, Fe-Fe3C and carbon curve, CO2C/CO, they intersect at L as before, but at the same time this L prime point is actually merging with L. That means these 3 curves intersect one another, these 3 curves at point L, and which corresponds to 63. That's 63 which is actually 63. So what is happening, as we increase the pressure, what happens? This intersection comes down to this point, L prime, okay? L prime. So here L and L prime same. So what is the achievement of this? This curve intersect at this point, and this is the invariant point. This is the invariant point, and where Fe 1 by 1, Fe-FeO and Fe-FeO, Fe3C and carbon. Fe-FeO, carbon, Fe3C and the gas phase which is shown on the y-axis are together, means 5 phases are together, and number of components already I have shown here. 3 component system, iron, carbon, oxygen. So 3 minus FeCO here, FeCO number of elements. So 3 minus 5 plus 2 is 0. So invariant point means there is no choice, automatically fixed. How it is automatically? Nothing. See, this temperature is actually where that meet this on unique temperature 1037, and also what is the pressure? P is just, it will be actually compulsorily, not arbitrarily, compulsorily, dependently will be 10.04. 10 means it will be actually. It will decrease the pressure, you will come back to this. Increase the pressure, again see it will happen, it will be lower. For this is coming down to down march, and if you still increase pressure, it will be, again it will be away from this curve. Okay, it will not meet, it will not intersect this curve at the meeting place. These two first two curves, carbon curve and Fe-FeO-Mn-MnO-O2 curve have met. Okay, so again, so this is a unique one, means no choice, no arbitrariness, no independence, no freedom. Another point is, remember here, so this is all about this. Okay, now okay, another thing is this, you see, this is they are at equilibrium. This temperature pressure, this is an actual pressure will be actually only no choice, will be 10.04, not 10.05, it will disturb. It will not make them together. It will not make these 5 phases together, means one solid phase will be out. So, and temperature is 1073. Oh, I'm sorry, 1037. So this is these actually are these 5, 1, 2, 3, 4, 5 phases together, as I have as I have already told you, and is shown here. So this is okay, this Fe-FeO curve. What I wanted to tell you here about this is the system. So okay, so this is okay, this is the this calculations actually last day I showed you there, and okay, very good. Actually, okay, how this curve is drawn. Say for example, Fe-FeO, CO2 CCO, perhaps I have shown you how to draw. Okay. But if you are interested Fe-FeO or say take up this Fe-FeO, these will be taken up when I will teach you how to construct stability lines, stability curves or stability diagram full. This I will show you how this curve is drawn. For the time being, actually this curve I have already drawn, but I will teach you. Not only Fe-FeO, other oxides I will take, iron oxides like Fe-CO4 magnetite and Fe-2O3 hematite also. So full-fledged iron carbon oxygen curve, I will teach you how to draw this curve. But today you accept that this is the curve, and then above this, above below, along the curve, Fe-FeO coexist, above Fe, below Fe-FeO. This part actually, maybe when I will teach you once more how to draw these curves. Okay, but carbon curve, this curve I have already actually explained you how to draw this curve. Okay, and I have actually discussed at length, and also I showed you how it is actually unstable zone, shooting, etc. above the curve or to the left of this curve. Actually, this above this side is actually of this curve, CO2 CCO curve. This curve, okay, this zone is an unstable zone, shooting zone. So above the curve or to the left of the curve, shooting zone. Okay, unstable gases. Okay, these are unrealizable gas. So this I said, but this I have not brought in here because not needed. Our discussion was how to show the independent point. Another point is this: you have noted here this state, or the title, caption, or this point. This is one. Here 0 degrees of freedom. Remember, 0 degrees of freedom will be shown by a 0 dimension. And which has the 0 dimension? A straight line, a curve, or area, or a space? No, point. 0 dimension, a point has 0 dimension, is of 0 dimension. So it is a point. At this point, coexist. This coexistence in this figure is this point, corresponds to this point. This invariant degree of freedom means no choice, hence a point, a fixed point. It cannot be any other point. It cannot be anything. If the moment you change the pressure or temperature or anything, then this 5-phase equilibrium will be upset. So this is actually this much I told you. So it is good idea that I help you with a few lines so that you have better information about this. Okay, you have a better understanding of this. I'm sorry. Okay, let us see. So start here. Stability diagram. Under this. Okay. So figure. Let me write. Figures 6B, 6C and 6D. 6B, 6C and 6D, depict the progressive development toward an invariant state which is F is 0 of the system as the percentage CO versus T plot, particularly note two things you note please. As we change the pressure, why it has changed from 80 to 68? Because these two curves, means I repeat, equation 2, equation 3. These two curves are subject to change when pressure is changed. They will be modified when pressure changes, these two curves. But not, at the same time, not this curve. Means which one? This equation 1. This curve. If this is unaffected by pressure, you can clearly see gas moles from the number of gas moles. 1 CO against 1 CO2 will not be affected by pressure, same number of moles. But here 1 CO2 against 2 CO, and here again similarly 2 CO against 1 CO2, so will be affected. These two will be affected. This is one point that I wanted you to note and to actually be careful about. And another thing that I tell you, 0 degree of freedom, a system with 0 degree of freedom will be, the equilibrium of a system with 0 degree of freedom will be shown by a point, because point is 0 dimension. System with 1 degree of freedom will be shown by a curve. Curve is 1 dimension. 1 degree of freedom, curve. Representation, curve, 1 dimension. And 2 degrees of freedom by what? By a area, region, area, which is 2 dimension. And you can go on actually, then you can consider space for 3 dimension. But okay, we'll be happy if you understand actually 0, 1, 2. 0, okay, what is called? It is 0, degree of freedom is 0, 1 and 2, and how they are represented. Okay, then actually we can use 2-dimensional figures to present them. Thank you. Particularly, so remember this, as the percentage CO versus T plot, particularly the CO2C CO2 CCO curve, which is equation CO2 CCO 2, equation 2, not only that, equation 2, and yes, and Fe3C curve, which is equation 3. Fe is equation 3, exactly equation 3. Equation 3. Comma. As the CO percentage CO versus T plot modifies when these things are actually okay. These things actually modifies. Modifies with the as I told you, with the change in pressure, with the increase in pressure or change in pressure, with the increase in total pressure of the system, pressure P, how it is changing? How it is changing? 1 atmosphere to next is 5 atmosphere to still increasing to 10.04. You bracket here. So 1 atmosphere. So this way this pressure has increased. The increase in the total pressure of the system these two curves are affected, but let us mention that Fe-FeO curve, this curve, or this curve, Fe-FeO curve will not be affected. Mention that the Fe-FeO curve which is also equation, right, alongside equation, which equation is it? Equation 1. Equation 1 is, however, unaffected by the change in pressure. Change in pressure, okay? In figure 6b, okay? In figure, start with this 6b. This is, remember, this is 6a. This is 6b, 6c, 6d. In figure 6b, drawn at, remember, What is the difference? Main difference 6B, 6C, 6D. How they are changed? Because pressure is changing. Which curves are changing? These two curves. Carbon curve and Fe-Fe-3C curve. The third curve, Fe-FeO curve, not changing, but the three things then are actually repositioning or relatively repositioning in such a way that at this pressure, at this particular pressure, they coincide. They intersect at a point. Okay, signifying the coexistence of these four solid phases: Fe, FeO, Fe3C, carbon, and the gas phase. 5 phases together. So drawn at. So what's the difference? Main difference: this is top line. P is 1 atmosphere. P is 5 atmosphere. P is 10.4 atmosphere. 10.04 atmosphere. Okay, therefore. So this drawn at P is 1 atmosphere. P is 1 atmosphere. The CO2C, the CO2C-CO curve. Sometimes we call it Woodward reaction, or is it carbon saturation curve? Carbon curve, CO2C-CO curve is given by the reaction 2. This CO2-CO curve. Why carbon saturation? I tell you, in this calculation, if you remember, we consider here, what is the activity of carbon we consider? 1. Means carbon saturated system. The equilibrium, this is the equilibrium, all lines are equilibrium lines. So carbon saturation curve, the CO2-CO curve, which is carbon saturation curve, carbon saturation curve, and what is the meaning of this? Activity of carbon is 1. Equation 2. Equation 2 and so this curve and the other one is Fe-Fe3C curve. Equation 3. Equation 3. Intersect at point L. Intersect at point L. Remember, this is written here. You see this? You don't see this? This is L. This is L. This is L dash. This line, this temperature and this temperature line and this curve, Fe-FeO curve, the lower curve, Fe-FeO curve, intersection is L prime. See here, L, when these two curves, top two curves intersect L, this is L prime. And here, these three merge. So L and L prime same. So only one name L. Intersect at point L. And what is that L here? Back to this figure 6b. Temperature 1037 Kelvin, and what is the percentage? 80% CO. So write this. These are the values. P is 0.10 means P is 1037 K, 80% CO. CO indicating the coexistence of Fe solid. As I have already told you, Fe solid, Fe3C solid, and carbon solid, and the gas phase, and the gas phase, and the gas phase. This point, not taking FeO, because here it is the stability region for Fe, not FeO. FeO is below this line. What we are discussing here, above this curve, FeO curve. Relative to FeO curve, with respect to FeO curve, this region is stable for Fe, above the curve. Below the curve, FeO. The CO with the percentage CO. So it is easy. CO increases, Fe will be stable. CO increases, Fe will be stable. And below, FeO. Opposite will happen. So Fe will be there. Fe is already there. Coexistence of Fe. No problem. But problem is, no, FeO is not allowed. FeO is dismissed. FeO is excluded. So that should be mentioned. And the gas phase, all are there. And the gas phase, FeO solid being absent. Being absent. That's right. According to your equilibrium. Now explain this. To the equilibrium of a FeO curve. FeO curve at 1037 Kelvin, any gas composition exceeding gas composition, that is in terms of percentage CO, exceeding that given by L prime which corresponds to 63% CO. Leads to the formation of FeO solid Formation of FeO as the stable phase, as the stable phase, and removal of FeO. FeO solid, FeO as stable, unstable phase. Oh, formation of Fe, I'm sorry, Fe as Fe. Please note this, Fe as stable phase and removal of FeO as the unstable phase. Unstable phase. Likewise, I'll come to this. I repeat this, what you know already. So what it says, since suppose they meet at 1037. So now see why FeO is missing in this equilibrium. Very easy. According to FeO curve, the upper part, the upper zone, upper region, upper region, that is the region above this curve. Above this curve is stability region for iron, and below this curve, the region below this curve is stability region of FeO. Since this is above this curve, actually in principle you say, suppose this temperature, this is the point, this is the critical point. Say any gas at this gas composition, FeO coexist. Both will be there. When Fe is there, FeO there. No problem. But this composition is not here, but where? Here. So, and what is our conclusion? Any composition above this will make Fe stable, and below this will make FeO stable. So, any composition above this, which is above, make Fe stable and FeO unstable phase. This is mentioned here. Removal. So FeO will be removed. FeO will not be there. Fe will be there. So Fe and Fe3C and carbon and the gas phase. So this is understood from this curve. Okay. So this curve will explain this. So next, likewise, this is about 6A. Then 6B. Now 6C. So likewise, in figure 6C, in figure 6C, 6C, drawn at P is total pressure, P means total pressure, is 5 atmosphere. Drawn at P is 5 atmosphere at point L. Here also similar at point L. Again here 60 here. Again L is the point. Again similar situation. Only thing, this point is lower here. This is corresponding to 68% CO. Previously it was 80%. So they also interesting. Again interesting. L. Intersection of CO2 CO curve, CO2 CO curve and Fe3C curve. So L. Same thing will happen, but only this will be, this point is now is closer to this L prime. L prime is L prime on a Fe-FeO curve, closer, and that is indicative of their merging, of their merge or their coincidence. Okay, if pressure is further, okay, of their merging, if pressure is further increased to what, 10.04. This shows that actually this is closing up. This point is closing up to this. When this intersection is closing up, means all phases meet each other at a point. This is the purpose. Likewise, in figure C, drawn at this at point L. Here also again same discussion at point L. At point L, which is T is what is that. Okay, point L coordinates T is 1037 unchanged. Pressure is what is this, percentage CO has changed. It's reduced to what value? 68. Intersection of these two curves. Okay, just point L. The point L means intersection of these two curves. Okay, AP3C and CO2CCO. So okay, 60. Okay, L at point L. Again, you can write AP3C. Again, similarly, carbon coexist. FeO solid and gas phase, and the gas phase also. Gas phase is shown on the y-axis. Why is the gas phase? Gas phase shown on the y-axis. Percentage CO means gas phase present. Coexist, again coexist. Similar situation. Again, FeO still not coexisting. Excluded. FeO still not. FeO solid. Still being absent. Still being absent. If we follow this development, this gives a clue what will happen. So if we increase the pressure, then as I told you, L is moving down towards L prime, is closing up to L prime, is moving towards L prime. So perhaps if we increase further pressure further, and there should be a unique value, mathematically calculable, and we have already calculated. So mathematically it can be found out. If further increase the pressure, this intersection L and L prime, it will come down further and will merge with the L prime and will coincide. Okay. So at a point, and these three curves will coincide at a point. We'll have a common intersection, point of intersection. Point. They will meet. They will actually have a common intersection point. If we follow the development, from figure 6b to figure 6c, it can be seen that tendency, what you are seeing that as tendency, that you can see that point L is moved closer to point L is moved closer to point L prime. Remember what is L prime anytime? First you see which temperature they intersect. These two curves, top two curves, 1037 Kelvin, and then which at that temperature, which point correspond to that temperature? Which point on the Fe-FeO curve? Which point on the Fe-FeO curve has that temperature means this temperature line and the curve intersection of this, which is L prime. At this temperature it has hit this Fe-FeO curve at L prime. This L prime on the Fe-FeO curve. So it is actually a different point. Yeah? But eventually, finally, it will be the same point. So 2 point it is moving closer to this, closer to L prime. As I have said, move closer to point L prime. Remember, L prime is what? By the L prime configuration is what? Coordinates already have the temperature is 1037 because that we wanted. And what is the value of percentage of 63? And remember that is unchanged with respect to pressure. No effect. No effect on the curve, Fe-FeO curve, because as I have already showed, no effect of pressure. See 1 mole CO and 1 mole CO2, same number of moles of gas. So move closer to point L prime. So L prime is what? How it is explained? I am giving you L is 80% CO. See here, follow this. L is 80% CO and L prime is what? What in the previously? L prime is 63% CO. It is 63% CO. This is in figure 6b. In contrast, in 6b, and if you again consider, and L is complete this, L is again, see what it has been, L has been 6 in the next 6C, curve 6C, 68. So L is 68% CO, while and L prime remains the same as 63% CO. So 68 closer to 63 than 80 is. So 8, okay. So in figure next, that is 6C, second figure, okay. First figure, second figure, third figure. We have not touched it yet. We have discussed, okay, explained, but we have, okay, formally we have not written anything about this. 6D has not come into picture, but okay, this actual preamble to that is also okay. The expectation of figure 6D is discussed now here. 6B and 6D. L is give a bracket here. This is how they are moving closer to point L prime in figure 6C than in figure 6B is explained here with data 6D. This suggests I am giving a star mark here. Star mark here. So I want to remove these lines. These 2, 3 or 4 couple of lines I will remove this. Okay, good enough. Let us write down. Gradually I will. So star. Stability diagram continued. Okay. This suggests a possibility of, okay, this suggests a possibility of coincidence of L and L prime as the total pressure is further increased, as the total pressure which is P is further increased. In fact, when the total pressure is total pressure is 10.04 atmosphere, this coincidence when the pressure is 10.04 atmosphere, this coincidence occurs. Okay, this coincidence occurs. And what is that? Refer to figure 6D. 6D. Yes, okay, figure 6D. This is everything is done, looks good, okay? This okay? Okay. Figure 6D. This is okay? This last line is okay? Is okay?
That is okay.
Where's blue? Huh? Okay. 6D. Figure 6D. This is 60. These figures with 60. Okay. At this state, this coincidence occurs, figure 6D, at this state L. We may call it at this point state. State is given by a point. A defined state is given by a point. Point is okay. But defined. So state or point, same thing. At this state L, all four solid phases, who are they? Tell me. All four solid phases, Fe, FeO, Fe3C, carbon. Actually, it is better I write actually, since they are already there. Fe3C, carbon. FeO was excluded, but now is included. And FeO will be in as well. So, and FeO will coexist. Along with the gas phase as usual. What is the character of this gas phase? What is the composition? C gas phase L 63 unchanged. So actually 63% CO already here 63, and this is changing. This L prime changing. This is L prime. Sorry, L is changing down to so 80, then to 68, and then to 63. So 63% CO. You understand this? Will coexist along with the two gas phase. This is an invariant equilibrium. This is this one. Invariant system, invariant equilibrium. This is an means degree of freedom is 0. No, nothing can be varied at will, arbitrarily. Okay, independently. Okay, this is an invariant. I should write here. This is an invariant equilibrium and characterized by F is 0 point. F is 0 point. Okay, this I will mention at the end. 0 degree of freedom corresponds to F 0 dimension means point. F is 0. Okay, which means invariant, which means this the variables, which means the variables. What are the variables? Tell me. For this L, we know everything. Everything we know. Temperature, for example, we start. Temperature 1037 Kelvin. All automatically, but all the same known, found 1037 Kelvin. What is the pressure? 10.04 atmosphere. What is the composition? 63% gas phase. And what is the composition for solids? They are all pure. Who are they? All 4 solids. Fe, FeO, carbon, Fe3C. All 4. Their composition are, since they are all pure, mole fractions of each is 1. Okay. So which means the variable, to mean the important variable is what? In the variables, notable, the variables, T, which means the variables T is what? T means variables T is 1037. Temperature, pressure, T is 10.04 atmosphere, and composition, temperature and composition of all phases. Well, gas phase I am writing, but all other phases, solid phases, pure solid. So pure means mole fraction 1 for each. So and gas phase composition. And composition is what here? Temperature, pressure, and composition. And composition, what is that? 63% for the gas phase composition I am talking about. 63% CO are automatically, very important. What we can, what else we can express with automatically? Okay, not okay. This is not independently. Automatically means compulsorily these values. Obligatory these values. Compulsory. Automatically this. No other. That's slightest change won't be allowed. No freedom. Or automatically I actually showed you in the previous day derivation. What is this? We call it demonstration. We showed how temperature is found, and then from temperature to pressure, and then composition, all completed last class, are automatically, not dependently, not independently, not independently, I'm sorry, not independently fixed. Fixed. This is okay. This is over. In a sense over. So just note here, additionally note additionally, this is over. Discussion is over. But additionally about that, what I wanted to tell you, 0 degree of freedom is represented by a 0 dimension geometry. What is that? Point. A point, as you see. And 1 dimension, 1 degree of freedom by 1 dimension means curve. 2 degrees of freedom by 2 dimension means area. Okay. So you note additionally perhaps additionally note additionally additionally an invariant state that is 0 degree of freedom, 0 degree of freedom, 0 degree of freedom is depicted by a point, which is of zero dimension. With this, we have completed example 6. Example 6 has been completed. So we'll take up, so this over, okay. So we will have to take up problem or example 7 next. Example 7 will be a different type. So this one, just put it back, okay. So start fresh. Sorry, example 7. So I have to change this, everything I have to change. This all changed. Remove this. This is not required anymore. This is not required. Just Gibbs space rule. We are discussing 7th example. Let us see how many we can complete today. Maybe 7, 8, as many as possible. But we think actually will barely finish 7 and add, and very optimistically 8. Wait a bit. Slowly, okay, just this actually not total, now it will be immaculate white, totally white. Now it is okay, and also you don't need this, you don't need this also, okay. This I will remove actually now. Let us start. It is better as we start this. So problem 7. Seven is what? Again, I am giving you the coexisting species as well as phases, Fe-FeO solid. But there is actually, now I am making a change here. Another system is not about iron, carbon, oxygen. It is Fe-FeO, then Mn-MnO, manganese. Mn solid, MnO solid. This is very easy, much easier than the previous one. Only one diagram will be enough. MnO solid, and obviously gas phase oxygen. Make a phase rule analysis of this. And if you ask me to draw this, okay, it's okay, very good. So start here. Here actually F is C minus. Well, this side is actually, yes, no problem. F is C minus P plus 2 U dash. Make a phase rule analysis means this actually examples will demonstrate. We'll find the degrees of freedom. We'll first find, then explain how by fixing a number of variables, the state of the system can be described in terms of temperature, pressure and composition of each phase at equilibrium. This is the job. And also with adequate diagram, okay, with actually assisted by some diagrams, this understanding, our concept, our understanding will be more clear. Okay, will be okay. Understanding will be clear. Okay. F is C minus P plus 2. This, before this, I should draw some sketches, though very repetitive, similar sketch, but still it is better we have a sketch. Because if you don't draw the sketch, you have to sketch it in your mind, inside your head. You have to think about this, how they are arranged, how they work together, how they coexist. So let me again, as before. So always I will actually draw this. This is the pressure, this is the temperature of the system, and who are present here, you will see. Fe solid, FeO solid, Mn solid, MnO solid. Okay? Not okay. Not okay. So MnO solid and oxygen gas phase. So 4 solids pure. These are pure solids. No solution. No solid solution or no alloy formation or solution, etc. So they are all pure. So this is the, and write always equilibrium. And mark it as figure. This is the setup as it. This is the equilibrated state. Figure what? 7a. 7b is kind of stability diagram. I will draw later. I will explain, and actually it's drawn here below. Here, okay. So start by finding the degrees of freedom and demonstrate how by fixing a variable the system is defined. So start. C is what? C, since here actually the reactions are not given, so go by elements only. C is number of elements. How many elements here? 3. How it is 3? What are the elements? Iron, manganese, oxygen. No problem. See, if it is C, also this C means now how many independent reaction equilibrium are there, you will find by applying the alternative definition of component. What is that? Number of species minus number of independent reaction equilibrium. How many species are there? Here we see 1, 2, 3, 4, 5 species. So 5 species minus, okay, 5 species. Oh, let me write this. It is better I write here. Number of species is 5. 5. Which are there? Which are there? Can I write here inside? Fe, right here. Copy from here. Fe-FeO-Mn-MnO-O2. 5 species, or number of independent reaction equilibria. How many is what? 5 minus 3 is 2, and write them out here. What are the 2 here? I can write Fe solid plus half O2 gas, FeFeO system acid, half O2 gas, half O2 gas is FeO solid. Call it equation 1 or reaction 1, and the other is 2 Mn solid plus half O2 gas is MnO solid, manganese oxide solid, which is reaction 2 reactions. Okay, I tell you, another can be written, another can consider, could have been considered. What is that? Fe plus MnO is FeO plus Mn. Repeat, Fe plus MnO, Fe plus MnO goes to FeO plus Mn. Will you consider 3 independent reactions? First of all, we have already found it is 2, and also suppose you write this, okay, as if you are convinced that the third will be there also. Now, but you know this is wrong. Wrong. Why wrong? Because this is actually obtained from these 2. This is dependently obtained. This is not an independent reaction. This is obtained from these 2. How? By eliminating oxygen. Eliminate oxygen, you will get this. So this is out. But I repeat, this is so important, I always repeat. It could have been possible you consider this as the independent. 2 only number is very important. 2. But who they are not fixed. This is a choice, matter of choice. So yes, if you consider this one, okay, and suppose you consider this and this, then this would be out. Any two. Careful about this. Don't ever forget. So remove this. Anyway, I have considered these 2 simple things as the 2 independent reaction equilibrium. So very good. Now consider, and then C is over. C is about C. Now what is P? P is the number of phases. P is number of phases. What are they? How many phases are there? 4 solids, 1 gas phase. 4 solids, they are all pure. So 5 phases. How you are getting 5? 4 solids and 1 gas phase. 4 solids. Will you write this 4 solids? Which are 4 solids? Right? Let us write it out. 4 solids which are there. Fe-FeO-Mn-MnO, 4 solids and 1 gas phase which contains only oxygen, no other gas but this, and 1 gas phase. Okay, 1 gas phase. Okay, that's good enough. 1 gas phase is oxygen gas. So 5 phases. So let us come back here. The Gibbs phase group. F is C minus P plus 2. What is the C? Value of C already we have got 3. 3 minus P is how many? 5 plus 2 is, oh, again 0. Again invariant. Equilibrium. Invariant equilibrium means 0 degree of freedom. System, invariant system. 0 degrees of freedom. The system, which system? The system containing all this. Under equilibrium is under an invariant equilibrium. And the system is an invariant system. So 0. Well, no choice. You cannot say I fix temperature. No. No, you cannot write anything in bracket. The temperature or pressure or temperature pressure or say mole fraction. No. Nothing. All will be settled automatically. Let us see how. Okay, 0 degrees of freedom, very good. So move on. So this is, and I tell you, so this might interest you. So 0, and this figure you see, and how they are shown in this figure. At the end, I will disclose this, but here now actually it might interest you. This point L, this point L, point 0 degrees of freedom L. L is the point or state. State. This is the state. L is the state at which all four solid, 1, 2, 3, 4 solid and 1 gas phase, oxygen gas is shown here in the y-axis, PO2 gas, and 4 solids are coexisting. So this will be at the end. So I am giving you the answer at the, okay. So this will actually, this will nicely actually, this is a reinforce our knowledge. This when you draw the stability diagram. But now mathematically we will find out, we will first complete this, that without fixing arbitrarily anything, how everything will be found out automatically. Let us start. Let us start with this last case guys, also demonstration. So I say what is the job? Next job is first demonstration, then actually I would say the okay, this stability diagram. Quickly, demonstration. Quickly start demonstration. Okay. What is this demonstration? You may underline this. What is to demonstrate? Okay, that as I am repeatedly saying, what you have to demonstrate? To demonstrate how by fixing m number of variables the state of the system will be defined in terms of temperature, pressure and composition of each phase at equilibrium. But here you cannot 0 degree. M number of variables means 0 number of variables, you cannot fix anything. Let us see how automatically it comes. Demonstration. So first is what I tell you here, start. Delta G0, follow me. This is pure math now, thermodynamic problem. Delta G0 1, follow 1, this is 1. Delta G0 1 is, you know, A plus BT. I always write A plus BT means delta H0 minus T delta H0. Okay, 2 term expression for standard of energy change. I will write A and B known quantities. A and B, remember, here A and B, delta H0 and B is minus delta H0, known quantities. On data book, okay, A plus BT is what? Continue, delta G is A plus BT is minus RT ln K T of 1, okay, KT1. What is this? You continue here, is continue minus RT ln, what is the equilibrium constant, right? Nicely see this one, activity of a Fe-O over activity of a Fe, solid actually, by PO2 power of activity of oxygen. You can always write equilibrium. You have no doubt, because these are all equilibrium constructions. These are all equilibrium. Okay. Ln PO2 equilibrium. So anyway, what is the activity of FeO? See, PO solid, okay. Yes, solid present. So PO solid is 1. Activity of iron likewise 1. So what you are getting from this is, you write this. Now actually I will remove this also gradually. Everything else pertaining to problem or example 6. So everything will be removed. Is what you are getting then? Tell me. Is half RT ln PO2. No doubt about this. Half RT ln PO2. Call it. So delta D. What is it? A plus BT is, okay, or A plus BT of RT. Call this equation 1, 2. This is third in sequence. Okay. Now similarly this time. Next, similarly delta G02, second is similarly, exactly similarly. Delta G02 A prime plus B prime T. It cannot be the same thermodynamic data, enthalpy change or entropy change. The different A is what? Again you write here, these are A and B, A prime and B prime are known quantities. A prime and B prime are known quantities. So you continue similarly, minus, just paraphrase what I wrote. RT ln KT2, just repeat. KT2 is what? You keep on writing, minus RT ln, what is equilibrium constant, write nicely for the second one, activity of MnO, Mn, PO2 power half, and you may always write this at equilibrium. Again this activity is 1, this is pure. So what you are getting from this? Half. What time? Tell me.
1 hour 33 minutes gone. 27 minutes still left.
33 minutes. Roughly 30 minutes.
Roughly 30.
It's okay. Thank you. Oh, you're right. 27 minutes. Exactly at. Is what? Half RT ln PO2 or you write once more, or you may hence this okay, and or write similarly A prime plus B prime T is half RT ln PO2. That will be your equation 4, and again we have no problem in seeing this, highlighting this as well. So 3 and 4, from equations 3 and 4, 3 and 4, what you get? See, right hand side the same in each case. So a plus bt, left hand sides are also same, is a prime plus b prime t, or t is what? What is the temperature then? Or t is what? Tell me. A prime minus a, b minus b prime. Temperature is hence, since these are all known quantities, a prime, b prime are known quantities, so this is known, found, temperature automatically found. Okay, is right. Exactly. Okay, known, automatic. As right here. It is better to write this. Is known. Right here. Automatically fixed. Right, known. Automatically mark the word automatically. No choice, no freedom. Only it must be this only. No other. Not a decimal change will be allowed. Will be allowed. Will not disturb. Slightest change, a bit of change, okay, not allowed. Smallest change not allowed. Okay, no. Some, okay. So this is actually no change. Change in the decimal places will not be allowed. So exactly this, automatically fixed. Not against, different from, opposite of arbitrarily fixed, independently fixed, automatically fixed. So temperature one down, then comes pressure, etc. So now from next, from equation 3, next from equation 3, where is this one? Equation 3, or maybe equation 4, as you like, or your choice, no problem. What you will get? You get PO2 is what? Equation 3, you get PO2 is what? Ln PO2 is what? 3 say, 3 you consider, 2 times PO2 is what? Ln PO2 I am writing. Ln PO2 is what? 2 times A plus BT by 2 times A plus BT over RT. This is what? You write this nicely, 2A by RT is 2A over RT plus 2B over R. Since T is already known, okay, T over R. Or PO2 is what you write? Exponential of this right hand side, RT plus 2B over R is known like this, is known. And again this figure is disturbing now. Okay, remove this figure. This figure is 6, about example 6 is pertaining to example 6. So is okay. Okay, don't do it. It's okay. Remove this. This okay. Now take up here is known. You can write here is known means automatically, right? Again automatically fixed. Automatically. No other pressure will be allowed. Automatically fixed. Happy, okay? Again, PO2 is fixed means PO2. What is PO2? As you know, okay. So let us summarize. So P is what? Temperature I know. P is what? Total pressure is seen only single gaseous species. Sole gaseous species is oxygen. So partial pressure of oxygen is same as total pressure. PO2 is PO2 is found fixed, known, fixed or known or etc. Tick mark. Okay, this is okay. XO2 is what? Always we write from this. Partial pressure is good. Partial pressure and total pressure means you know the mole fraction. What is that? P by, but still composition in terms of mole fraction. Mole fraction is what? PO2 by P, since they are same, is 1. So gas phase composition is over. Total pressure is over. Temperature is over. So okay, this is 1. This is 1. So what is the solids? About the solids, other phases, all solids, pure solids. So you can write this pure APO, and what else present? Pure APO. What you should write? This leads to pure APO solid. This leads to XFE. Mole fraction wise is 1. We'll study later this iron manganese in solution. This will study maybe next problem. Maybe next problem. But in that case, it will be mole fraction. You have to write this. Mole fraction you have to consider, and mole fraction is not 1 because that is impure solution. Okay, but so allow for that pure solid. What is the mole fraction? We know very well, but you write this. XAP is 1. Mention this. XAP is 1. Pure APO, right? Similarly, pure APO solid. This leads to XAPO. Mole fraction is 1. Pure Mn solid means XMn is 1 and pure MnO. In fact, next problem we will consider Fe-FeO-Mn-MnO also in solution and FeMn in solution. Oxides are in solution. We have typically called slag phase, so oxide phase, and iron metal phase. Pure iron and iron and manganese will enter into solution. We make a solution, so making themselves impure or okay in the solution state. They are bringing themselves in the solution state. What is this? The mole fraction will be in that case, that which I will discuss in the next problem, will not be 1 anymore, will be less than 1. That we will discuss. Okay, pure, but now currently this pure MnO solid, which is XMnO, leads to 1. So all temperature, pressure, composition, all known automatically, even though we have no freedom. We cannot even start with temperature, say fixed temperature. So like this, unlike previous cases where we consider say temperature and then we used to write equilibrium constant KT, etc. Anyway, this is actually good exercise. No, this is not over. So the remaining part is what? Okay, these are require some discussion. This requires some discussion. I tell you something. Okay, quickly I want to finish this. Problem 7 at least. Okay, quickly, not much time left. Okay, maybe 15 minutes or so. So please follow. ln PO2 versus 1 by T. You recall this first problem, first example. Metal plus oxygen is metal oxide. What I plotted? Recall ln PO2 against 1 by 2. Against 1 by T produces a straight line, negative slope actually. And this I have done. For two cases I have separately drawn two lines. This is obtained from the example 1. So this curve for Fe-FeO for this reaction 1, equilibrium 1, and the other one, this is also the negative slope Mn-MnO. These two curves. Now again see, given this, so it is easy. So you go back to this example 1 and you see these curves I have drawn. Now what is the stability? Domains, etc. Stability. So what does it mean? Along this line, follow one by one. Follow. What is the name of this curve? AB. Fe-FeO. You consider letter Mn-MnO. FeO, this curve. AB. So along this curve, Fe-FeO coexist along with the oxygen pressure. The plot is ln PO2 against 1 by T. Then if you plot this way, then a straight line will be generated, and it's convenient. If you plot a PO2 against 1 by T or temperature, non-linear, a curve will be generated. Non-linear. But linear you prefer. So that's why ln PO2 versus 1 by T is very typical, very common thing. So curve. Now along this Fe-FeO, now tell me, as PO2 increasing this way, okay, so if you increase the PO2, which will be stable? FeO. So above this curve, FeO, below Fe. Below Fe. Similarly, below Fe means why? Because if you decrease the oxygen pressure, then FeO will dissociate and FeO will be eliminated, iron will be stable. So Fe below, FeO above. I have written on the this side also. Fe, FeO. Above, below. So this space, above this curve, forget about the other line, above this curve, or you may say to the right of this curve, whatever you may say, above this curve, FeO is stable. FeO is stable. Below, Fe. Similarly, Mn-MnO, what is the name of this curve? CD. C, you don't see well, CD curve. Okay, straight line. So you are also negative actually. So CD, this slope will be dictated by the delta H0 value. So here, A and A prime, the delta H0 value. So CD curve, again here it is along this curve, along the line, who exist? Both coexist. Mn-MnO. Above the curve, MnO, below Mn. You see, again on the either side you may write this. So below Mn, see here MnO I could not write MnO I have written here. But actually you follow this. So you easily follow. In this segment, what is they intersect at L. Okay, L. Okay, I will explain this. L corresponds to temperature T1 and pressure P1. Pressure is dot. Pressure is PO2 is P1. ln PO2, from which you get PO2, P1 and T1. Okay? Don't worry. So this is very easy. From this side and that side, they intersect. So and this is the answer. Where actually this equilibrium will be described by this point, 0 degrees of freedom. This is the answer. Why all phases? Let us see. Follow. You see one by one. In this segment DLB, follow me. What I write here, CD. Start from this. DLB, who is present? Above this curve, I said what? FeO. And according to this curve, below, who is present? Mn. So this region will be reserved for FeO plus Mn. These two phases will coexist. Repeat. Follow one by one. Follow according to this curve, AB curve. Above the curve is who is present? Fe or FeO? One of them is FeO. FeO is stable. And below, this region I am considering DLB. So it is above this curve. So FeO. And again, follow this curve CD, which is for Mn-MnO equilibrium, reaction 2. Below this curve, this region means below this curve, who is stable? Mn. So in the segment DLB, in this region DLB, who is present? MnO from that side and FeO from this side, or FeO plus Mn. Similarly, take this region DLA. So above this curve, which is stable? As above this curve, in this DLM is this region. Above this curve, which is stable? MnO. And here from what are we getting? The MnO from this curve, and from this curve, which is stable? FeO. So FeO from this side, MnO from that side, FeO plus MnO. Both oxides will coexist here in this domain. Domain is DLA. Similarly, tell me ALC. Who is present? Clearly, so below this curve, FeO curve, who is present? With Fe. And above this curve, who is present? Who is stable? MnO. So it is Fe plus MnO stability field. And now last one, BLC. This one, this. Who are present here? Means this is below this curve, means Fe present. And this is also below this curve, means Mn is present. So Fe plus Mn. So two metal phases together. Fe plus Mn. Very easy, very nice also. This is Fe plus Mn, both metal. This is both oxide. And here one metal, the other oxide. Namely, here it is FeO plus Mn. Metal Mn plus FeO. And here opposite. Here Fe plus Mn. This segment and this segment. So this will be discussed. This will be actually now maybe written. What I will stability diagram. Quickly take up this stability diagram construction. So I think I should write where. Let us start here at figure 7b. Stability diagram. Shall I write here? Right. Quickly. 10 minutes. Okay, 10 minutes is there. Shall I remove this? Okay. Shall I remove this? This part is over. Okay, let us start writing stability diagram. Quickly. Means this one, figure 7b actually. So figure 7b is the stability diagram. Okay. Let's start with this stability diagram. Okay. ln PO2 versus ln PO2 versus 1 by T. Achha. For reaction 1, right? For reaction 1, or you may call it equilibrium. Which one I first consider? 1. Equilibrium 1. ln PO2 versus 1 by 2 plot is linear. That is linear. That is line AB. That is what line? Line AB. Line AB. Where you see it? Figure 7b. Line AB, figure 7b. Okay. Recall example 1. How will you get this? Recall example 1. M plus half O2 is MO. You may look back. Recall example 1. The slope of this line. This slope being linear is linear right here. The slope being what we know about the slope, as much as I know, it is negative and also related to delta H 0. So it is proving slope being negative, governed by the delta H 0 value of reaction 1. since we are discussing for equilibrium or reaction 1, for reaction 1. So for reaction 1, okay, is okay, is okay, this one. Similarly, actually I don't actually have to be. I think I need this. It's better I remove this, huh? I remove this. I don't need this. Okay? Similarly, quickly, for reaction like this, exactly like this. For reaction or equilibrium 2, actually here is 0, I am writing this side is 0. Remove space, equilibrium is 0. For similarly for reaction ln PO2 versus 1 by ln PO2 versus 1 by T is again linear. Line, which line? Line C, this one, CD, line CD, with the slope being negative, exactly like this, being negative, bound by the delta H0, value of reaction 2. This delta H0 is A plus BT here actually, A and A prime, the known quantities I said, this is actually the delta H0. Now, actually it is better I remove this, huh? I remove this. It is not because this is over. So quickly write down few things, okay? So quickly, 5 minutes I shall take. Lesson 2, start here. In figure 7b, follow this. As I have already explained, so I am just writing only now. In figure 7b, above line, as I have already explained, so I don't repeat. Above the line AB, who is stable? FeO, you know, FeO solid is the stable phase, above the line is the stable phase. Remember, along the line both, above one, below the other is the stable phase, and below the line and below above line AB, below line AB, and below line AB, and below line AB, AP solid is the, and below line AB, AP solid is the stable phase. So this is okay. This is about AB. Likewise, tell me CD. You tell me CD. Above, below. Okay. Likewise, above line CD. MnO solid is the stable phase. And below line CD, who is the stable? Mn. Yes, Mn solid is the stable phase. Is the stable phase. The two lines intersect at point L. the two lines intersect. The two lines right here. Okay, remove this. This is all over. The two lines intersect at L, at point L, at point L. It follows that in the region DLB, you see, DLB, this one, where FeO plus Mn is stable, mixture is stable, FeO plus Mn in the region DLB, the solid mixture
2 hours, 1 minute, 27 seconds.
Or another 3-4 minutes, 3-4 maximum, no? In the region DLB, this solid mixture, who are this, right? It follows in the DLB solid mixture, Mn plus FeO. Yeah, this one, Mn plus FeO. Mn plus FeO is stable. Similarly, in the region DLA, who is stable, FeO plus MnO. Similarly, in the region DLA, the solid mixture FeO plus MnO is, so remember FeO plus MnO, keep it here, comma, better. In the region, similarly, continue. In the region, next, in the region, what? ALC. In the region ALC, which one? Fe plus MnO. In the region ALC, the solid mixture Fe plus MnO, and in the region last one is CLB. CL means this region. C in the region means region in actually region means CLB means below. This region I have said CLB. This region means this enclosed by CLB etc. enclosed. Okay. You understand, I hope. CLB means this region. DLA means this region enclosed by DLA. It is also enclosed. This one in the region CLB. It is written also here. CLB, the phase mixture, the solid mixture. Solid mixture, Fe plus Mn are stable phases. Hence, at point or state, whatever you call it, point or state L, point or state L, all four solid phases, okay, all four solid phases, which are the FeO, Mn, MnO. Also for solid phases, along with the gas phase, which contains only oxygen, which is O2. Shared by oxygen with the gas phase with the gas phase are at equilibrium. Means 5 phases are equilibrium as we consider there. Okay, are at equilibrium. Okay, the temperature and pressure at LR. So let us the temperature and pressure at LR automatically at LR are automatically fixed at T is T1 and PO2 is nothing but the total pressure as well as total pressure is P1. Where it is shown here, please follow me. What is the T? T is T1. What is the PO2? LNPO2, get LNPO2 from which you will get PO2. So PO2 is P1. When PO2 is PO2 is the total pressure, is what value? Each of them is P1. So PO2 is the total pressure, is P1 value. Okay, LNPO2, not LNPO2. You will get LNPO2 from which you will get PO2, and that is call it P1. Okay, PO2 is P1. In compliance with automatically fixed, underline automatically. In compliance with a 0 degree of freedom. Okay, with a 0 degree of freedom. So we are all set, we are happy, very much happy. Again, note once again, note here. Again, you have a difficulty. Okay, note once again. No difficulty. So, 0 degrees of freedom. 0 degrees of freedom, and hence a point described by a point, 0 dimension. Again, like last time, like last example, almost 1 minute, less than a minute. So note once again the invariant state. Once again, like last example, the invariant state. 0 degrees of freedom, 0 degree of freedom, 0 degree of freedom. That is invariant state is represented by a what? By a point. By a point, which is that L, 0 dimension. Point is L, 0 dimension. So 0 degree of freedom is represented by 0 dimension. L, by the point L, which is of 0 point as a 0 dimension. So we are very happy. Okay, here what is this? This is removed. Fe-FeO is okay. This is FeO. Okay, it is FeO. Thank you. With this, we have finished example 7. Is also over. Thank you very much. Okay, for giving me some time. Okay, and we have exceeded. Okay, overshoot 2 hours. Anyway, thank you very much. We have finished after all example 7. So we'll take up example 8 next day. 8, 9, 10, etc. 11, 12. So thank you very much for your cooperation and for your interest and sincerity. Thank you. Okay, see you in the next class. Bye.